Okay, so another sort of general topic on acid and base, kind of this catch-all thing, is these polyprotic acids that we have seen along the way. So we've seen some of these acids that have more than one hydrogen that can lose. So we've seen like sulfuric acid, right, H2SO4, or phosphoric acid, H3, PO4, right? These acids that have more than one hydrogen that could be lost. Now, the key is that these polyprotic acids ionize in steps. So they don't lose all 3 hydrogens at once or all 2 hydrogens at once. They lose the first hydrogen, then the species that's formed loses a second hydrogen, etc. Right? So there's a stepwise. And each of those equilibriums has an ionization constant. Now, typically, as you move, the size of those ionization constants gets smaller and smaller as you go to losing more and more hydrogen. So the first ionization constant is the largest, the second one would be smaller, etc. Now, for most of these, we only really have to worry about the first ionization constant because it's enough larger than the other ones that it produces the bulk of the hydronium ions, so that we can sort of negate the amount of hydronium produced from the second or third ionization. Kind of like when we have a mixture of acids, we can typically ignore all but the strongest of the acids. So, for most cases, that's the case. Now, one notable exception to this is sulfuric acid. H2SO4. And in this case, we do often, if we were to go and solve a problem, with sulfuric acid, we do need to consider typically more than one ionization sometimes. So it really just depends. So most cases we can ignore anything beyond the first ionization, sulfuric acid being a notable exception to that. Now, just to kind of point out some of these and sort of draw your attention to this trend. So the reason why sulfuric acid is important is because it is one of our strong acids. So the first one essentially goes 100%. So the second one, is significant because the first one is, 100%. Now, for all of these other ones, they're weak acids to begin with. So the first one, the K1, might be on the order of what the Ka2 is for sulfuric acid. So let's say, phosphoric acid, right? And notice the second one. We're changing by typically, 5 to 6 orders of magnitude. Now, there are exceptions, of course, and there's some where you're going to find it, but typically there's, a fairly significant difference between the magnitude of Ka1, Ka2, and you can see if there's a Ka3, it gets even smaller. And so, typically, if we solve the first Ka, that's going to give us the bulk of the hydride, and solving for the second one isn't going to add any sort of appreciable hydronium ion. So if we do look at that sulfuric acid example, we can see here that our first ionization, right, is strong, right? So 100% of this becomes this. Now, our second ionization, right, is the product of our first one, so our, again, undergoes a second ionization, in this case to produce our SO4 2- ions plus some hydronium. So we got hydronium from here, hydronium from here. And because of the size of this, right, typically it produces a significant amount and we have to count for it. So if we want to calculate this, it's simplified a little bit because we know the first one goes all the way. So if we take the initial concentration of this ion is going to equal the concentration of our original acid, because this goes fully to this, and so we know what that is, so that means we know what that is. And so this then is going to give us our hydronium ion, initial hydronium ion concentration that we're going to use when we solve this equilibrium. Now, I'm not going to, worry about this at this point. I'm not going to go through and solve this, but the idea is, the first step here, we can calculate how much hydronium is because, we know that this hydronium is going to be equal to the original H2SO4. So that's what's there in the beginning. So when you set up your ICE table, right, and we have our H2SO4 plus water plus, instead of this initial being 0, right, this is going to have an initial concentration, right, coming from here. So it starts out at this level, and so when you go to solve for this second equilibrium here, you can't have this as 0. You have to have it as whatever is produced here. So you can go through this, and then you can solve this equilibrium, and that'll give you the ending, or after the second equilibrium, what the overall hydronium ion concentration is. And they go through this in the book, but at this point, I don't think it's worth our time for you to do it. There's a whole lot of other things for you to focus on in terms of getting comfortable doing these equilibrium calculations with all these different kinds of acids and bases. But we should at least know that sulfuric acid is kind of an exception, that we can't just ignore everything else and just look at the first ionization like we do with a lot of these mixtures and polyprotics. Now, just one last thing to put this sort of again in a more pictorial. So this is a weak acid. Right? In the first one, we produce this much hydronium. In the second one, we produce, in this case, this much hydronium. If we were to add up the total hydronium, what you can see is it's essentially equal to what we got here. So when you have these, differences in the amount produced in the first and the second, what you really see is that any hydronium produced in a later ionization is really insignificant compared to what's produced in that first ionization. So it's a little justification of why we can ignore everything that comes after that first ionization, again, except for sulfuric acid. Okay, so polyprotic acids.